Now on this page, we'll talk about a third property of R. The ones we know so far, just to recap, are: one, units of measurement do not affect the value of R. So the example we saw, if you change from feet to meters or something like that, it's not going to change the value of R. Also, we should only use R when the form is linear. If the form is not linear, it's some kind of curve that's not linear, then maybe you'll see in another statistics class or a class in the future what to do then. But this R that we're talking about in this module is only used for linear relationships. Now we'll examine a third property of R. We cannot determine form from R. So the correlation by itself is not enough to determine whether a relationship is linear. In other words, we cannot determine the form of a relationship by looking at R. So we kind of already have to know that it's sort of linear, and then we use R. It's not like we calculate R and that will tell us whether it's linear or not. So we really have to graph first. Graph, or plot the data, I should say. Graph data values, the X and Y coordinates, and then determine if it's linear by that. Linear, or approximately linear, I should say approximately. And then use R. If so, use R. Just to find, that'll help us find the best fit. Okay, so here's an example. R is close to 1 and does not indicate a straight line. So this is an example of, if you were to find R first, and you think, well, that if it's close to 1, that means it's really a really good linear relationship. That's not true if you can't tell if it already looks like a line based on the graph itself. Let's look at a situation where an R value that is close to 1, but a relationship that is not linear. Recall the study in which participants were paid to complete a survey. The study examined the relationship between the amounts of the monetary incentive and the percentage of the sample who returned the survey. We had 1 point way over here, so it looks more like a curve that kind of goes this way. If you're familiar, it might be something like a logarithm, log-based something like that. That could be the function that models the data. Anyway, that's kind of looks like that graph. It definitely doesn't look like a line. It kind of looks like a line in the beginning, right? These data values here in the beginning, and then it starts curving the wrong way and kind of flattening out as you go to the right. So probably not linear, I would say. Probably not the best model for it. But if for some reason you found out what R was first, you said, oh, you misremembered what R was for. I'm going to calculate R. If it's close to 1, that means it lines up in a line. But you have to make sure it's linear first before you calculate R, and then it just tells you how good the line would represent the data. But the relationship is not linear. The form is curved. The correlation alone does not tell us whether a relationship is linear. We must always look at a scatter plot of the data before using R. Here are 2 more examples to emphasize the point. When R equals 0, for example, we'll take a look at 2 scatter plots below. They have a correlation coefficient of R equals 0. We cannot interpret R equals 0 to mean a weak linear relationship, because we see a very strong curve relationship with R equals 0. So if you already suspect that a line represents the data well, then you calculate R. So in this case, R would be 0. That would mean, okay, never mind. This data is kind of probably too random to even use a curve or a line to represent the data. It doesn't really line up very well. But here, if you think, oh, well, it lines up kind of well, let me see what R is. Well, R equals 0, but that's because it's not linear. It's not because the data doesn't line up well. It lines up well. I guess I shouldn't say lines up, because it makes it sound like it's a line. But it all falls on the same curve. There are no outliers at all. They're all lying on the exact same curve. So R equals 0 might not necessarily mean that the data doesn't lie on the same line or curve. It just means, yeah, that a line wouldn't represent it well. But that's not to say that a different kind of curve would represent it well. Now we'll look at an example where R equals 1. Let's see. Take a look at the 2 scatter plots below. They both have a correlation coefficient close to 1. We cannot interpret what R close to 1 means in that it can't mean a strong linear relationship. It's only if you already think it looks like it lines up in a line, and then you could say that close to 1 means it has a strong linear relationship, because we see the data set without a linear form can also have R values close to 1. So you should, like we wrote above, we should plot the data. Once I plot it, if I see this rightmost graph, I wouldn't even think that could be construed as looking linear, not even close, right? So I wouldn't even bother calculating R, but if I did, it would look close to 1, and it might, if you forget what order you're supposed to do these steps in, you might accidentally think that a line can fit this data well. On the other hand, if I were to plot the graph, or all the ordered pairs that are in the left-hand graph, then it does look fairly linear. I could tell it's not going to be R equals 1, It'll be R equals a positive number because it's sloping upward to the right, but it doesn't look, definitely doesn't look like anything but a line. I don't think a curve could fit this. It would be a line. And that's why the R equals 0.98. It's close to 1. In that case, it was used correctly. That I saw that it looked like a line. I calculated R. It is close to 1, so that's a good line, or whatever it is a good line. But the other one, maybe even though R is close to 1, it doesn't look linear at all, so that doesn't tell me anything. It has to look linear, first of all, but also it has to have a R value close to 1 or -1 to be a good fit for a linear equation modeling the data.